Okay, I guess here we are to start off our last session here. Let's see, let me make sure my audio's doing what it should. Looks like it from this end. Let me know if it isn't from yours. And we're going to go over the homework. Where'd it go? There it is. And let's say mention a couple of things here since this is the last session. I sent a posting out from the website, and you should have gotten an email that pertaining to both the final and the project. Finally found there actually was a page in the on the slides here that had to do with the due date. The stated date on there said 2 weeks from the final lecture, and what I said in the email there is, okay, well, let's go ahead and make that 2 weeks from today would be the due date for the project. If alternative commitments over the holiday period and such make that difficult or something, let me know. I'm sure we can work out alternate arrangement. The final, I haven't gotten my act together completely on that. I'll post that when it's ready. I'll certainly give at least a week in order to do that. And if I happen to post it at a time where it's inconvenient for you to do it within that week, I guess let me know, and I can probably work out something there too. So let's see. I think that's pretty much the story. Other than let's go through our last homework assignment here. Let's see. I made some minor changes to the handouts, which included clarifying a couple of things on the homework here. I think I actually did state them verbally in the last session, but it wasn't obvious from what was written on the slide here. So the assignment here was to take the MCMC samples and, well, actually I've also mentioned a complication here, but in the original thing I said take the MCMC samples from ME Hands-On 2 and use them to do two tasks. One is to simulate the posterior median and 90% credible intervals for the population mean effect, and do that by time. Well, you're basically doing it by time and dose and presenting it as plots of effect versus time by dose. The other job was to simulate the posterior median and 90% confidence or credible intervals for the population mean effect again, but now do it versus concentration. And as I say, in this case, just do it overall. Don't stratify it by dose. And then specify the doses to include in your simulations, the concentration range in there. And I didn't actually mention it before, but my presumption is that we're actually dealing with just single doses here, and the time range that I was going to recommend here is 0 to 24 hours, and that too I didn't mention last time, but alternatives would have been fine. And in the end, to just present these then as plots showing those posterior medians and 90% credible intervals, and they'd be plotted either by time or concentration, depending upon which one of those two. Now, the one thing I realized afterwards is I wasn't entirely thinking, because you actually cannot do the first problem here to get the posterior simulations for the population mean effect by time and dose based only on ME2 Hands-On 2, because the reason for that is the dependent variable in that model was concentration. It wasn't time or dose. So in order to be able to do the problem, in order to be able to get the population mean effect as a function of time and dose, you'd have to somehow also incorporate predictions for the concentrations based upon time and dose. And you actually have done that, but not in the context of ME2 Hands-On 2. You did that in terms, I say misspelled that. There should be an on in there. You would need ME2 Hands-On 3 in order to incorporate the pharmacokinetic component. So that was actually a little more complicated than I was originally thinking, but I'll show you a solution that in fact does take both pieces of information to do this. But as I go through this, where I'll start actually is, let's start with the second problem here, which is to work with the posterior distribution for our population mean effect versus concentration, and do that first because that's actually the simpler problem. Okay, let's sort of put that aside here. I also posted on the website a solution to this in here, but let me go ahead and walk through that. I've got it here in the form of an R script for doing it. Here we go. ME hands-on to sim.r. Let's open that up. And make it a bit, make it a bit bigger. Okay, so let me sort of point you through the tasks that we're going to do on the problem here. So the basic idea then, and I guess maybe bring up the slides just to use as the framework here. So we're going to be doing, we're going to be specifying a range of concentrations, and then for each one of those concentrations we're going to simulate we're going to simulate values from the posterior predictive distribution for the effect here, which was factor 10A inhibition. And recall, in fact, let's step back to the algorithm we're going to have to use. Recall this is a population model, so we've got inter-individual variation as a component of this. So we're going to go through a process like the one shown here. And in fact, let's see what's the structure. Somewhere in here I mentioned the structure of the model we're working with. Okay, and the structure of the model we're working with is actually very much like the one I've given here. In fact, I think it's well, almost like it, except for the covariates in here. So we've got a model where our factor 10A inhibition would play the role of this Yij here. And as I recall, it is in fact normally distributed in our model. So the right-hand side would be consistent with that. For our Y hat here, the expected value for the factor 10A inhibition in an individual at a particular time, or actually following a particular concentration, is sort of like the right-hand side, except instead of having the Tij and the Di and the Dj here, that would be replaced then by, I guess we'll just call it a Cij. So that would be the concentration. Well, in fact, we don't even really need the subscript I and J in a sense, but we're going to be plugging in particular concentrations as our covariate in there. So that would be the main thing that changes there. And again, we have some random effects in here represented by the theta j, which come from a multivariate normal distribution. So we're working with that same basic structure. And let's remind you also what the model looks like for this case. Let's go back all the way to hands-on 2. Okay. Oops. So here's the specific model we're dealing with then. So we've got our factor 10A inhibition represented by the E here. And again, that was normally distributed. Our E hat then is a sigmoid Emax model. And we've got one random effect, one inter-individual random effect in here. That's for our EC50 parameter, and that's log normally distributed as described here. So we're going to be simulating from that model, given pre-specified values for our concentrations. So that's your basic job is, one, go ahead and generate a grid of concentrations that you want to make predictions for. And as you recall in our specification of the problem, we want them to cover the range 0 to 1600. I believe that's nanograms per mil in this case. And given that, and given the posterior distributions or posterior samples for all of the parameters in here, generate the posterior, well, actually we didn't specify the posterior predictive distribution for EIJ here. What we're actually going to do is for each sample, for each posterior sample of our various parameters, we will calculate basically a population of individuals. So a population of these EIJs, and then take a mean of those values. And we're going to loop through our posterior samples and do that for each one of our posterior samples, and then describe the distribution of those means. Okay, so let me go back to the basic algorithm we were just looking at. Okay, that was posterior predictive, which is not what we want. We want our population simulation, so something like this one. So again, our outer loop here is looping over our posterior samples. So in the construct we're going to have inside of our R script here, we're going to have a matrix containing our posterior samples, where each column corresponds to a different parameter. In other words, a different element of this theta hat here. Well, actually theta hat, omega, and sigma will have, all of those will be present as columns within this matrix, and then the rows will be the different posterior samples. So we're going to be looping over that. And for the mth row of that matrix, then we're going to do this. Let's see here. Let me know if you're having any audio problems. I just got a little red posting on this that suggests I might have some connection difficulties here. Okay, well, let's see. So far nobody's complaining, but let me know. Actually, let me fire up my Skype in case somebody tries to reach me that way. Okay, well, that's going on. So for each one of those, so for the mth column in here, we're going to go through this second loop. So you can see where it says for for j equals 1 to n pop, so n pop is that big number which would be something large enough to give us an estimate consistent with maybe like an infinite number, but of course we're not going to do infinite, so we're just going to pick a fairly large number there. And so from that we're going to have to sample, just a moment here. Okay, I think I'm okay. Sorry, I was just checking some connections here. Let me just check one thing real quick here. I think we're okay. Okay, so we're going to sample our thetas, so we're going to get individual values of our model parameters here from our normal distribution. We then take what in our case is going to be that sigmoid Emax model to calculate the individual specific expected value, and then finally generate predicted observations from our residual variation component of our model. So we do that for this hypothetical population of individuals, and then the next step is to calculate it says the appropriate sample statistic. In our particular case, that appropriate sample statistic is going to be a mean. So we're going to be taking a sample mean of that. So we do that. So we're going to get, for each concentration level, we're going to get such a mean. And then we go back and start our loop all over again at that point and go to the next element of our posterior until finally we have a number of means for each one of our concentrations corresponding to this end post value then. So that's the process we're going to be going through in our script. So let's go back to that. So one of the first things we have to do is construct a function that actually can deal with some element of that simulation process. And in particular, the part that I'm going to focus on initially is to basically do what's inside this inner loop. So I'm going to write a function that does that process. So in fact, in a sense, it's taking care of, it's actually taking care of that loop plus taking the mean at the end here. So it's basically everything that's inside the outer loop is going to happen inside this function. So that's this function that I'm highlighting right here. So that's what we're creating. Here I called it just FXA mean sim, so that's going to be generating our percent inhibition of factor 10A activity given a parameter vector. So that's going to contain all of our all of our fixed effects parameters as well as all of our variance terms. Then the sigma component I referred to over here is actually buried inside of this P here. And in fact, actually I just computed. P contains all of it. So we got omega, sigma, and our thetas, if you like. Then we're going to pass in our covariate values, which in this case is going to be a vector of concentrations that we want to do simulations at. And then finally, this end sim in this case represents the equivalent of what I called end pop. There it is, end pop over here. So it's the number of individuals to simulate. So again, that's the number you want to be relatively large enough such that the sampling variability does not result in too much error in this. Here, the way I did it here is I went ahead and first I generated my individual level values of EC50, because recall the only random effect in this case we had was for EC50, which was log normally distributed. And here you can see our mean is the log of what was saved in the original model is EC50 hat. In here, and then there was what was called omega EC50. In fact, you know what I should do here actually is bring up the original model so you can see the naming conventions we had used in that. Let's see, I want ME hands on 2. There it is. Let me bring that in here. Let's move it to a different window. And change the format and make it bigger. Okay, so what I pulled up here is the WinBUGS model we had used for ME hands-on 2, and it's just reminding you here you have we have log EC50 in here is distributed normally, or equivalently EC50 here is distributed as log normal distribution in here. The other thing I should probably bring up as I'm thinking of this here is let's also pull in the R script so that you see what was actually saved. just remind you here, in this one, notice that the parameters that were saved are listed here. So these are the quantities that when we pull up what was saved previously, when the bugs run was done, as the parameters are going to be named, we'll have the EC50, EC50 hat, so that's our median basically for our population median for EC50. We've got our gamma, sigma, and then omega dot EC50, which is the standard deviation associated with the inter-individual. Well, it's the standard deviation for inter-individual variability in EC50, but in particular, actually for log EC50. So those are the parameters we actually have to work with here. Okay, so let's go back. So you can see how that we're generating the individual specific values of EC50. So for that, you can see this is going to be, there'll be what, n sim such values here, so to work with. And then what I'm doing here, I think of this S-apply as being like a for loop. And it's looping over all the elements of the concentration vector that was passed. And for each element of that concentration vector, so for each concentration, it's taking, that concentration, it's taking our the one row from our posterior distribution of parameters, and it's taking our whole population here of EC50 values, and it goes through and first calculates what I called FXA hat. That's going to be the individual specific expected value. And notice on the right hand side is nothing more than our sigmoid Emax model over here, where you can see the concentration showing up here, and then you see our individual specific EC50 value crops up here. And inside this, the way I set it up, keep in mind EC50 is this vector corresponding to however many hypothetical individuals we're simulating. So this FXA hat will also be of the same length in there. And then the next step is to, there are two steps here. One is I'm generating the individual sort of the predicted values, because this is describing our residual variation, and then taking a mean over all the individuals, all those individual predicted values. So in a sense, what's happening with this internal part is that's generating a distribution of observed values for individuals, and then taking a mean in here, and then that's what was going to get reported back. What'll get reported back is actually going to be a matrix of values coming. Actually, will it be a matrix? Let's see. Yeah, it will be a matrix of values that'll come back, and I forget which is going to be row and which is going to be column here, but one of them is going to be have a dimension of the that's the same as our. Well, actually, I'm sorry, I'm forgetting here. We're only doing one row of our posterior at once, so I'm sorry. No, it'll return a vector in this case, corresponding to a mean for each one of the concentrations that gets passed in. Let's see, what else do I need to tell you about this before we go to the next step? Well, first of all, I'll mention that the idea here is the way I'm going to use this function subsequently is to take that and then put it inside of a loop that loops over all of the rows of our posterior matrix. So it's going to step through all of those rows. Each row is going to correspond to P, the P argument in here. So, and when I do that, then it's going to generate this whole distribution of predicted values for each one of our specified concentrations. Let's see, okay. Check something real quick. Okay, no problem. Okay, so let's start with that. So that was sort of a key component in the simulation process. Most of the junk on top is the usual kind of bookkeeping stuff for path names and that. And because of what we're going to do, I need to have access to the results of both ME Hands-On 2 and ME Hands-On 3. So that's why you see reference to what I referred to as PD model name and PK model name in here. For our first problem, we really only need the first one here, the PD model name. Example name is just the name of the directory that I've stuck this particular script in. And then I've created directories down here that are pointing to all of these things. Let's see, nothing too much going on here that's new other than bringing in a particular library that has a multivariate normal distribution as part of it, because we're going to use that as part of one of the simulations we're going to do. Let me skip some of this stuff that has to do with the second part of the problem. Let's see, here you can see in this statement, okay, right here, this is just telling the program what I'm going to want to save out of the posterior matrix when I read it in, and that corresponds to the parameters of our model. And then right here is just a statement that is going to go out and get the results from ME Hands-On 2. Let me point out in our files, when you do ME Hands-On 2, so you've got the overall directory that contains the ME Hands-On 2 problem. When you run it, it creates another directory inside of that of the same name, and inside that there's this object right here called ME Hands-On 2.fit.r save, which is a binary file containing R objects. In this case, it only contains one object, and it's that bugs.fit object that we create when we run the problem, and that contains all of our MCMC samples. And that's what we're reading in with this load statement right here. So we're reading that in. The result of that is we'll now have that bugs.fit object, and down here I'm just taking the sims array component out of that, converting it to a matrix instead of this three-dimensional array, and then the next step is just extracting only the parts of it that I need, namely this set of parameters right here. Okay, let's skip the PK part again there. I open up a PDF file to contain my plots, and here's where the business end of things is. Recall I said do this for a range of concentrations going from 0 to 1600. It's up to you how finely divided you want to make it. Just to keep the computation time down here, I put in 17 for the number of concentrations to do simulations at, which in this case then is going to be every 100 nanograms per mil we get a simulated population mean. And then the next step right here, that's good, is to generate that sequence of concentrations. So when I run this, you'll just get, basically for consts will be a vector containing like 0, 100, 200, 300, and so on up to 1600. And then here finally is where the real business end of it is in this one little statement does a lot of stuff. I'm using the apply command, so that's like a for loop that loops over either the rows or columns of a matrix, our matrix being this PD posterior. If this number here is a 1, it means it's looping over the rows. So that's what we're doing in this case. So for each row of this matrix, it runs this function. And it runs that function in such a way that the first argument of that function will be a row from that matrix. So that's how it works. And then I have to specify any of the other arguments. And recall that in addition to that P argument, which will be that row of parameter values, we have our concentrations, and however many individuals we're going to simulate, and I just picked that sort of round number of 1,000 in this case. So we'll go ahead and do that. So when I run that, I get that big matrix. Let's see, that one isn't too horribly lengthy as I recall. Let me go ahead and actually, I don't think I've opened up an R thing, have I? No, I haven't. Let's go ahead and do that. Just opening up an R process here. Let's just stick that over there. Yeah, let's go ahead from the top here, and I'll just go ahead and run this right on down, load up all our files so we don't have to monkey with those later. Let me do everything but the prediction first. Oh, you know what? I'll bet there's something I need to change. Yeah, I need to change this so that it's consistent with the way my machine's set up. Okay. One more time. Okay, let's make sure that flies okay. Actually, while that's running here, I'll also mention, apologize, I haven't gotten the recording of the last lecture posted yet here. Got lots of excuses, but it's not there. It'll probably get posted either later today or tomorrow. I finally managed to get it sent over to the office. Unfortunately, it takes a while because they're about 2 gig. Sometimes they're about 2 gig files, which this one was. Okay, so that ran. I don't think there's any errors here. Yeah, it looks like that ran okay. Okay, so let's go ahead and do the prediction step for this one. It does take a little bit for that to run. It's not horribly awful, but keep in mind that you're running, in this case, essentially, what do we got? We've got 1,000 individuals we're simulating. For each time we call this, we've got 3,600 rows or things. So we got what, 3,600,000 simulations of values, basically. Oh, actually worse than that. Then you got to multiply by 17 for the number of concentrations. So it takes a little while. Let's go ahead and fire it up. What happened? Oh, I see. No, it's fine. Fortunately, when we go to the next example, though, it's a little bit more complicated because of having to bring in the PK data. The core principles are the same, so we don't have to spend quite as much time explaining. Actually, that ran faster than I thought. We give you some idea what this looks like then. So if we look at the, let's do the str thing here for pred. Okay, so you can see this is now an object that it's a matrix. It's got 17 rows and 3,600 columns. The 17 rows correspond to these 17 concentration levels that we've simulated. Let me see. I can't really do a head because that's not going to look at it. Let me just give you a quick look at the part of it here. So we're talking like, let's do pred. Well, we can actually do all of the rows, but just to do a few of the columns here just to get some idea, give you some idea what it looks like. So you can see here, I guess I sort of ran it over. Let me widen this a bit. Okay, so you can see, I guess it's just a bunch of numbers basically, but you can see in particular we've got our 17 rows. You can actually sort of visualize here. So for example, for this one, for the first column here, so that is a result of taking the first row of our posterior distribution. You can kind of see how here it starts out with a a mean that isn't a whole lot different from 0 down here and goes all the way on up to about 93. So that's showing our concentration effect relationship. So that works. Oh, I just realized something I didn't mention. Let me just point out before I forget again. For this particular example, notice here that this was the function that I had used to get our population mean. I actually did one step that we don't really need in this case, and that's what's going on inside our mean right here. Because we've got because we're dealing with a distribution that is symmetric in this instance, it's symmetric, and it's mean. You know, the expected value of this thing is actually the very parameter we put in here, this fxa hat. So I actually didn't need to take this do this normal sampling right here. It would have been sufficient just to take the mean of the fxa hat. And I actually would have ended up with a little bit more precise result, and it would still be an appropriate representation of the population mean. So that actually would have been appropriate in this case. So I've overcomplicated it in this instance. Now that statement is pretty much only true for the kind of case that I just said, where you're trying to get the mean of something which has a symmetric distribution. If I wanted to instead ask for something like the standard deviation, the sample standard deviation, or maybe one of the quantiles, then that statement wouldn't hold. I would definitely still have to do this, include the residual variability as part of it. Okay, so we got our pred there. Now, this pred is actually giving us a fairly complete representation of the posterior distribution here. So for any one of the concentrations that corresponds to the rows here, if I wanted to look at what does that posterior distribution for the population mean look like, I could simply do like a histogram or density plot of the values in that row. But for our purposes, what I'm going to do is present the results instead in terms of credible intervals. So let's go ahead back down to where we were. Okay, so we had, make sure I get the right one. Yeah, we had just run this statement right here, this pred statement. So first of all, in order to use the particular plotting routine I want to put this in the form of a data frame. That's what's going on here. Well, there's a couple of things. One, I'm putting it in a data frame, and two, as you can see inside this mess right here, I'm taking quantiles. In particular, I'm getting the 5th, 50th, and 95th percentiles of the pred values from each one of those rows, and those are the things I'm actually going to plot. So this is just a bunch of bookkeeping here to generate those quantiles and organize it into a data frame that also contains the matching concentrations and appropriate labels for the statistic, whether it be the 5th percentile, 95th, or the median. Then the next statement here is just ordering them appropriately so the plots actually show up in the appropriate order. Let me go ahead and fire that up here, make sure that runs okay. It did. So let me go ahead and do the plot. Okay, so I'll run the plot. I won't go through a treatise on lattice plots. I'll let you agonize over any details there that you might want to learn. Feel free, if there are questions that you have on any of those, I'd say feel free to maybe ask the questions in the form of an email, and I can respond to that. Okay, so we've created that plot. Actually, we can't really look at it without turning our plotting device off. Let me actually try this here rather than doing that. Maybe we'll open up a little plot screen here, and let me see if I run that again. Will it use that, or will it put it in the PDF? Yeah, okay, that's what I wanted. and this is the plot we wanted. So we've got, it's the population mean versus our plasma concentration. You can see the curve here. In this particular case, we apparently our parameters were estimated with with fairly high precision. The end result is our population mean prediction is pretty tight in here. In fact, I was a little surprised when I saw this. I'm still tempted to go back and double check and make sure I didn't make some errors in here, because I thought there'd be more uncertainty in our parameters than this. But assuming I haven't done something silly in the calculations, you can see we ended up with fairly high precision because the 90% credible intervals for our population mean are quite tight. Okay, so that was really the first, or actually the second exercise that I had specified. Let's go back to the problem I specified here. Okay, so that was the one here where I said simulate the for our population mean versus concentration. Now the first one, as I said, it turned out to have more complications than I was thinking at first, where it says simulate for our population mean versus time and dose. And in order to do that properly, we really have to also generate the posterior distribution of the concentrations, and then use those as the drivers for predicting the effects. I suppose a crude way that we could have handled that would be to do something like simulate, take the observed concentrations from the that were in our data for ME Hands-On 2, and sort of do simulations for each one of those individuals and then take means over that. But that wouldn't represent exactly what we want. It'd be an approximation to what we're doing here, but it really doesn't appropriately consider all of the uncertainties, because that would be a prediction that's consistent with the finite set of patients we had in that study, but it wouldn't consider the uncertainties due to the fact that we're actually trying to make inferences about a broader population. So the approach then that would be more, I guess, a more rigorous strategy would be to do this as sort of a two-step process where for each time and dose combination, I would simulate the posterior predictive distribution for our concentrations. For each one of those simulated concentrations, I simulate a predicted effect, and then I take the mean over that. So it's a two-stage process in here. So let me show you how I constructed that. So let's go back to the top here. Recall that we've got a second model here, our ME Hands-On 3 model, which was a population PK analysis for our ME2 drug. And I'm going to use the PK model that was done there. So that was our two-compartment model with first-order absorption that we have there. So we've got another function to deal with that in this case. So what you can see here is just a function right here that just does our good old-fashioned two-compartment model given a set of parameters, P here, time and dose. So you can just see sort of the standard calculations for that two-compartment model here with, I guess I threw in the units adjustments here for 1,000 to go from liters and hours to get us into, I guess it'd be kind of milligrams and liters. Let's see here, or micrograms and liters, sorry. So you can go through and look there, make sure I didn't make any silly mistakes. It's just intended to be as I say, the standard two-compartment model in there. So that will do that. And then I created another function similar to the one we just did above that's going to make use of our simulated plasma concentrations. In this one, I'm allowing for, well, P should be a single vector containing our parameters. Time and dose, the way I've programmed this, can both be vectors, but they have to be vectors with the same length. So that's the assumption I made when I was writing this. So we can construct all possible combinations of dose and time that we want to make predictions for and go ahead and pass those in then as vectors here. I suppose I could have made them a data frame or something like that instead. And again, we've got nsim for our number of individuals that we're going to simulate to create our population mean. First part of this is just a little bit of bulletproofing here to check whether time and dose really are equal length vectors, and if they're not, it stops the program with an error statement. Next step is to generate our PK parameters from their inter-individual variation model. And if you recall, in this model, all of the parameters are clearance Q, V1, V2, and Ka were the inter-individual variation model on that was a full multivariate normal model. So I took the parameters that corresponded to that, and here's where that multivariate normal distribution comes in. So there's, by the way, the multivariate normal is not built into the standard R, but there's a couple of different libraries out there that contain a multivariate normal random number generator. The one I picked here, RMV norm, is contained in the MVT norm library, so that's why I read that in there. Okay, so here that's where I'm doing it. So all of them are actually, they come from a multivariate log normal distribution, so that's why you see the log transform here and then the back transform there to get our parameters here. So what's going to come out of this is this PK par is actually going to be a matrix where the columns correspond to the different parameters and the rows will be, well, there'll be nsim rows there corresponding to our different hypothetical individuals. In this here, just for subsequent bookkeeping, I'm adding column names on here. Actually, I'm changing the column names from the ones that are up here to this clearance Q, V1, V2, and Ka. Then I do also I sample from my inter-individual variation model for EC50. So we deal with that. So there's our PD. So we got our random effects for both our PK and our PD model. In this case, I'm generating the same number of individuals for both. Since the models were run independently, we actually don't know anything about whether there's any possible correlation among individuals here. So we're at this point assuming there isn't, but that's an assumption at this point. And then finally, we do that whole simulation process down below here. And let's see, so again, I'm going over what I'm saying, this loop right here that's created by this sapply statement is now looping over those vectors of time and dose. And here you can see I'm actually looping over a set of indices that go from 1 up to the length of the time vector, which is equal to the length of the dose vector. So that gets passed as the first argument of this function here, which I just called I, and I'm passing in time, dose, my row for my posterior matrix containing the parameters there, and then my individual specific parameters that I called EC50 and PPK right here. Notice that these names don't always match what's up on top. The matching is taken care of down here by the set of arguments to sapply. Most of them I actually use the same name, but in this case I didn't here, so I've got PPK equals the PK par, which is what we defined up here. Let's see. So, and inside this loop, the first step I do is generate the plasma concentrations. So this is now for, so this is going to be a set of plasma concentrations for a particular time and dose, but for NSIM individuals. So this const will have a length of NSIM, because that's the length of the EC50 and the PPK components here. So that's generating my concentrations. Notice it's calling that 2CPT sim function that I had up there. So it's generating that. So that's generating the expected values. And then I've also got the residual variation model for the concentrations. Also comment here, normally when I do a simultaneous PK model, I would probably use the predicted concentrations or the sort of the predicted expected values for individuals as the driver for a PK model. But recall that when we built the PK model here, we were using observed concentrations. So given that, I felt it more consistent to use the predicted observed values that also include the residual variability as the link in this case rather than the expected values. So that's why incorporating that here. And then the next step is bringing in then our sigmoid Emax model that uses the concentrations that we just simulated in here, and finally taking our taking our mean over all of those individuals to get our population mean. So again, what we're going to get out of this is we're going to get a set of population means. This is going to, so for any one call to this function, you'll get, let's see, you're going to get, the number of values you'll get will be the same as the length of the time and dose vectors that you pass in here. And then what we're going to do down below is we're going to call this function once for every row in our posterior matrix to then generate a distribution of values, our posterior distribution of those mean values. So let's scroll on down to where we use that. Let's see, that's in the, yeah, here we go. So here what I've got is I'm pulling in the times and doses that I'm going to use for the prediction. The doses I specified in our specification for the homework. The times I didn't, but in this case I just used the sampling times that were used in the original study, the phase 1 single dose study, that is. This step right here, there's a handy dandy function in R called expand grid. And what I've done here is notice what I pass to expand grid is I pass our time vector, and which I called TOBS up here, and our dose vector. And what happens is expand grid is going to create a data frame that contains all possible combinations of these times and doses in here. So it will take care of that for you. Then I say, let's see, for my NSIM, instead of picking a hard number, because it was possible that I did a different number of samples for the PK model and the PD model, what I chose to do is for NSIM I picked the largest of the two of those, and well, down below I'll show you how I sort of rectify that later on when we do the sampling. So I do that, and let's see, what am I doing here? Oh, I just had to take care of I use the same name sigma for the residual standard deviation for both models. So here I renamed the one for the PK so that I would not make the mistake of using the same name twice. Let's see here, and then we generate our, oops, what I did is I combined the two posterior matrices, the PD and the PK in here, and I sampled randomly from those in here in order to match them up, and where I ended up using that NSIM values in here. Let's see, and they end up just getting matched randomly instead of matching the first one of one with the first one of the other. They get sort of jumbled up. Not sure that makes much difference here, but that's what I chose to do. And then finally, it does the simulation as the next step here. Let's see, where do we end on the others? Actually, while we're talking about it, let me go ahead and have it run, because that one does take a little bit longer than the other case because of the PK simulation part of it, and the fact that we're doing more cases in here. Make sure that's actually running properly. That's not what I wanted to look at. Where's my R? Yeah, it's running. Okay. So I'll do that, and the same old deal. I'll pull it together in a data frame, order it appropriately, and then make plots. And we'll take a look at that when it actually finishes. If it seems to take too long, I've actually got a completed case in here we can take a look at. I guess I would encourage you to take a look at some of the details I've kind of jumped over here. They're always, especially if you're using R as a regular tool, you might find some useful tricks here and there on how to work with some of these elements, particularly if you're not used to using things like the apply and sapply statements, because they can be useful because they tend to run faster than for loops, though I will admit they're not as easy to read as for loops. Actually, while that thing's running too, this would be a good point if you've got any questions to go ahead and pose them. Actually, maybe I will go ahead and show you go ahead, and if you want to post a question, go ahead and do it. But in the meantime, why don't I go ahead and pull up the runs that I actually did before. Oh, that's right, I can't show you them. That's okay. I only wanted to show you this one anyway. Okay. So this is actually what, when it finally finishes, this is what the thing will look like here. So you can see what I've plotted here. Notice down here, and I'll show you before I show you that, actually the plot function, I'm saying plot or FXA, which is my factor 10A inhibition, versus time, and then this thing, this upright bar is essentially going to plot that by dose. So it'll have a separate panel for each dose level in here within the plot. So, and you can see that here, so you can see the doses up here, 0, 1.255, and so on up to 80 milligrams here, and you're looking at the concentration effect plots. And again, just as before, our uncertainty in our model parameters, or at least in the predictions, was relatively low. So you can see our predicted population means are actually fairly narrow in these things. And that was pretty much the exercise I wanted you to learn how to work with. The other thing, if you wanted to take this the next step, is for both of these cases, you might also want to take a look at the posterior predictive distribution for individual predictions. In fact, I could have done this so that would have been something of a side effect of what we're doing here, but chose not to do that and just focus on the population mean. And you'll see there, for example, that these credible intervals will be much wider because now you're making inferences about the probable range of values for individuals rather than what a mean would look like over individuals. So it would also, so when we take the mean, we basically stripped out the inter-individual variation whereas we're only really showing uncertainty here, whereas when you do the posterior predictive distribution for individuals, you also have that inter-individual variability reflected in the plots. Yeah, still going. So they say that one, in fact, I haven't even calculated. That's quite a chunk of simulations you've got, because because when you do all possible combinations of times and doses, you end up with, I don't know, you'd have to count those out. And what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those, and what is it, about 18 or so of those. So you got, what do you got? 180 different combinations or something like that in here. So that takes a little while to run. If you want to do testing on these, I recommend doing fewer of the combinations and knocking this NSIM down, just to test your programming here before you actually do a full production run. Okay, I think that's going to be pretty much it, and I guess it's pretty much it both for going over the answers to this, as well as for the course itself, other than for those of you taking it for credit and doing the final exam and the project. Look forward to seeing those. I've actually already got a couple of the projects turned in, so I'll be looking over those shortly. Look forward to seeing more. Not much more to say other than I hope you found the course useful. And if there's more you're interested in terms of some of these sorts of Bayesian applications, we've got a couple of other courses that we teach that are logical follow-ons to these. Do one on model-based meta-analysis, where I do use WinBUGS as the primary tool in that course also, as well as a course in categorical count and time to event data modeling that we offer. In fact, I think we're offering, and I'm forgetting which were the specific courses we're offering. It might have been those two that we're going to be offering sometime in the late spring as an on-site course. We were originally going to offer them as web-based courses in the next semester, but unfortunately we didn't get enough enrollees, so that's why we're going to be doing it as just on a sort of a single occasion as an on-site course, and see how we do there. So I guess that's it, and again, I look forward to seeing your assignments, and good luck, and have fun doing some Bayesian work. Keep your eyes open for new and maybe easier to use Bayesian tools. In particular, I expect to have the BUGSModelLibrary simplified somewhat in the not too distant future, though I don't have a formal target date at this point. So thanks again, and hopefully maybe I'll see a few of you around at meetings. Bye for now.